Okay, so I really appreciate your having me here to talk. So I should say I'm not a meteorologist and I'm not a climatologist, and I'm going to explain the reason that I got interested in this problem, which is going to be slightly more abstract, maybe, and it will include things that go outside of the bounds of the subject, but hopefully I'll explain something. So okay, so here is my preamble. So nonlinear ODEs and PDEs have long been the stalwart of physical modeling. Many of us grew up on these books, and I just sort of, just for fun, I gave you a list of books. So, this is the Collège de France. I felt like we should have a truly mathematical book. So there's ODEs by Arnold, which is a wonderful mathematical book. And then the three to the left of it are sort of on different subjects where ODEs and PDEs come up. The center one, of course, is on atmospheric modeling by Jacobson. But there's also rheology and there's molecular simulation. And I guess that is, the way that it's always been is that when I was a student and we teach our students, like, you will learn about ODEs and PDEs because you will use them to be able to understand the world around us. And that's what we've always told our students. But I think if we're honest, we have to admit that, that recent results from the ML community, and I think, some of which I think probably gave rise to this meeting, on important scientific questions have called this dominance into question. And I want to sort of point to two papers from DeepMind. One is Remy's, who will talk about it in a little bit, and I'll mention it a little bit, is on probabilistic, but then there's also AlphaFold. And both of these problems are problems where I think it's fair to say that the physicists, I'm kind of a physicist, we would say that, well, you should go and write down the ODEs and PDEs and solve them. But yet, it is a fact that protein structure prediction was not solved by a force field. And I think it's a striking fact. And in fact, these have, and again, people should disagree with me, basically no physics at all in them. There's no underlying differential equation, and they are more accurate. I mean, the AlphaFold, I never believed as a mathematical computational scientist that it was possible to do a calculation that was so precise in a field with so many experiments around that would actually be so precise that you would sort of 2 years later win the Nobel Prize. Like, that's just astonishing, as a mathematical computational scientist. And so the question that I want to ask is, like, how is this going to play out? I mean, we've all, I don't know, I have books, I have shelves. You guys have shelves full of books about these things. Do they matter anymore, and how are we supposed to think about this? And but if you look at these books, I just want to point out a couple of things. These are different books. So this book, the Arnaud book, is pure and elegant. Actually, that maybe has nothing to do with it. The only thing it has to do with this discussion is that I think, Arnaud, what he would have said is that, well, the reason you should learn about the mathematics of dynamical systems is because of how general it is. And then he probably would have started talking about the weather. I don't know. And it's the latter part that it's called into question. Now, the three books to the right, though, are much more messy. And they are actually filled with, if you open them up, if you have the courage to open them up, and I guess today we're opening up the second one in a certain sense, they're just filled with ad hoc parameterizations. It's filled with muck. I don't know how to say it. It's just muck, basically. And so there are these beautiful equations, and then they have muck. And just to sort of give you ideas of the muck, I just want to make sure, and maybe you all know this, but it's a really general phenomenon of the muck. So, parameterized force field. So you can go and say, well, people have been doing molecular dynamic simulations of proteins for some time. There are two major potential projects. There are more, but there are two that are out there. One is called AMBER, one is called CHARM. CHARM actually was started by a person at Harvard named Martin Karplus, who passed away a couple of years ago at the age of 95, and he won the Nobel Prize for this. So that was pretty good, but the point is it didn't predict anything. Maybe that's unfair, but I think that's pretty accurate. And you can kind of see why, like, that's the potential, it's just muck. Like, it's completely fine, each of the terms you understand what it means, but the point is if you imagine that there's a different parameter for every amino acid, or every pair of amino acid, then like, you have to fit them all, and it's just a mess. And in fact, people, the hygiene is what I would say, of the physical science community fitting these parameters, it's substandard. More on that in a minute. And then, of course, there's the topic of today, general circulation models, which consists canonically, I just copied the equations from the MIT GCM as an example of a set of conservation laws, and then, I don't know if does this thing work as a pointer? Oh, it's the front button. And then there are these these innocuous f sub h, f sub r dot, q sub, and these are like these innocuous functions. But those functions are 100,000 lines of Fortran code and they've been worked on for a long time and they contain like lots of stuff about like what the physical processes are that is basically parameterized. And then just to throw another field, this is very common. Rheology is a subject which I think is kind of interesting. It's like you add a right-hand side to the Navier-Stokes equations to model more complex fluids. And this is a table that I took from a really beautiful article that was written about a year ago by Howard Stone that sort of writes down the general rheological formula, which again has these kind of innocuous looking f of c, lambda of c terms in it. And it's just a mess, basically. And so, for any fluid, what are the parameters? People argue. So I guess what I want to suggest, and this is the thing that this is the issue that I'm most interested in, how I got into the Neural GCM, which I will spend most of today talking about. But I think the death of dynamical systems as a paradigm for complex systems is perhaps premature. It may not be. It may be that what we're seeing here is, I think one of the interesting things about weather and climate is that they're really precise things that one can predict. And the question of how to predict them, what is the mathematical model that one should use? The level of complexity is that of anything else. So what I want to say is that this is whether it's premature. This is an empirical question for how to best model complex systems. And the point which kind of gave rise to what I'm going to tell you about is that if you want to fairly compare a pure machine learning model, either AlphaFold or one about the weather or the climate, with a PDE with parameterizations in it, you have to train the parameterizations with the same level of technical rigor and attention to detail as was done in the pure ML models. And this is a point where I think the physical science community, not the ML community, has really lagged behind. And so that's the thing. And I just did one more part of this introduction. So David Donahoe wrote what I think, if you haven't seen this, maybe this is the most interesting thing from my talk. David wrote what I think is really a beautiful position paper about a year ago called Data Science at the Singularity, in which he says, everyone's going nuts about AI. But then he says, in my opinion, AI singularity is a misleading narrative which can't explain a wide range of new developments. I will argue that something fundamental has really changed, driven by three principles of data science, namely data sharing, code sharing, and competitive challenges. Namely, you will share your data so everyone can train on the same data. I think you will see among many of the speakers today, well, at least Remy and I, we were training on the same data. Like there's data sharing, code sharing, please make code that others can use it and modify it. And competitive challenge, please compete on real metrics and be careful about how to do this. And what David argues is that these are the things that have kind of led us to the situation that we're in, not just with respect to what we're talking about today, but even, arguably with respect to language models and whatnot. And I guess the thing I want to raise here, just as an abstract question, is whether or not we can still save PDEs. I might be the only one in the room. Some of you must want to save PDEs. It's France. Yeah. You guys must want to save PDEs. I don't want to give them up. So that's the thing. So we've in this purple box. So what we've done over the last couple of years is to undertake a research program to carry this out across a suite of problems in different domains. So PDEs, general circulation models and rheological models, and ODEs, coarse-grained potentials of things. Because I still, and what I'm going to do is tell you about a little of that today. I'm going to mainly focus on general circulation models because of the name of this meeting, but I'm going to talk about some of the work of a graduate student who just defended his PhD thesis on this, which I think it hasn't gotten as far as it needs to, but I think it's interesting and it raises some of the same mathematical issues. So here's our approach. It's very kind of simple-minded. So what we do is we start by writing a physics-based simulator in a differentiable programming language, because what we want is not to train a pure machine learning model. What we want to do is take the laws of physics that we know and love, and we want to use those, but we want to train the parameterizations, and we use JAX. So one can, build, JAX versions of molecular dynamics engines, CFD solvers, models in biology. Then the second step is to choose a design goal or an objective function. Namely, I would like to build a parameterization to reproduce the following data. And then the third step, and this is, common in machine learning as well, is we're going to then use a gradient-based optimizer to find the parameterization. of course, the beauty of automatic differentiation, and also the same as the adjoint method, is that the cost of computing the gradient is independent of the number of parameters. So this can be done very efficiently, even for large numbers of parameters. And then the idea is to develop new models for systems that can't be modeled accurately, and then to see how they do, in the landscape of predictions. And so, another comment that I'm not going to comment on, I'm going to say, but I'll just say once and I won't say again, is another nice thing about this approach is that there are lots of scientific problems which are optimization problems, and when you approach science in this way, then there's also just many optimization problems that can be solved now that were impossible 5 years ago, which I think are pretty interesting. So that's basically what we do. And the goal, as I said, is really to improve the state of the art and the accuracy of computational models of complex systems, including the ability to assimilate diverse data. And within the world of people who love ODEs and PDEs, as I do, the goal is to try to start to create a culture of iterative improvement with measurable performance benchmarks in exactly the same ways the machine learning community has done so successfully over the past 15 years or so. And so that's the thing. So with that as a preamble, my talk is gonna be divided into 2 parts. And I'm like really bad on time, and I should also say, just in full disclosure, I wrote this talk on the plane last night. I mean, I did have some slides, but I put it together, so I can't promise coherence. I actually have maybe reframe. I have an excuse for my lack of coherence. I don't know if people ask questions here, but you should feel free to ask questions, and I will, Stefan, wherever you are, please yell at me if I've talked too long. Okay, so what I'm going to do is spend the first half of the talk talking about the Neural GCM, and then I'm going to talk about this problem, which is not part of this meeting, but I'm going to argue that the sort of mathematical problems are really quite similar, actually. And I think it provides a different, interesting example. And then I have here a list of other systems that are of this flavor that we've been working on that I'm not going to discuss today, and I just put them up in case anybody wants to talk about them after. So the Neural GCM. So we are interested in creating neural weather models. I'm really glad Remy is here. I don't know which of us should have talked first. Neither of us chose. So Remy is going to give it a fascinating and I think quite complimentary talk, and I'm going to try to set this up correctly. But you should definitely yell at me if I say something you disagree with now. Although I guess you can yell at me later. So general circulation models are the basis of traditional weather and climate forecasting. This goes back a long way. Lewis Fry Richardson in 1922 wrote a book on weather prediction. And then, there was this Nature review article in 2015 that is called The Quiet Revolution of Numerical Weather Prediction, in which forecast skill was sort of increasing over time. Like the weather forecasts were getting better and better. What does a weather forecasting system look like? So the best weather forecasts in the world, at least until recently, were by ECMWF, the European Weather Forecasting Agency, and their principal model is called the IFS, the Integrated Forecasting System, that basically includes sophisticated data assimilation of the Earth system to make predictions. And they actually have medium range forecast, extended range forecast, and long range forecast. The medium range forecast, I'm going to actually talk about medium range and extended range in this, not really long range. But medium range is up to 15 days. And so I don't know, the way I think about this is that, when I was coming here on the plane, I wanted to know what the weather was going to be in Paris, and my phone told me 2 weeks. So that's 14 days, 15 days. So now AI models in weather forecasting have been gaining tremendous skill recently. This is an example of an arbitrary plot that one could make of this. So this is a plot of skill relative to ECMWF IFS. So skill basically means how accurate is it relative to the other model. And so it's like, the difference in errors between the model X and that model normalized appropriately is what the y-axis is, and this is time. And this there are many quantities that one can measure. I will expose this a little more in a minute, but this is the 3-day forecast of 500 millibar surface height, which is a reasonable variable. And basically, over time, the skill relative to ECMWF-IFS was growing. These were all pure machine learning models. There was an interesting model by Keisler, which is the first person to introduce graph neural networks in this in about 2023. And then in the last couple of years, the thing has really exploded. So Pangu was the first model that basically was able to beat the ECMWF-IFS at 3 days. I should say, actually, the Lyapunov time of the weather is about 5 days. So you can get away with a deterministic forecast up to 5 days. The problem changes qualitatively after 5 days because the problem is stochastic, and so one needs an ensemble. GraphCast was a DeepMind model that was a deterministic model. And then what I'm going to talk about is the Neural GCM, which is a hybrid model. I will explain what that means. And then there are lots of other dots. And one of the dots in here is GenCast, which Remy is going to talk about. I guess Remy's probably going to talk about both GenCast and GraphCast. These are both fascinating models. I actually don't regard this point cloud, you shouldn't, it's just a point cloud. The point is they're above the orange line, and basically, I mean, I have the impression, and actually Remy maybe will comment on this, or we're going to disagree on this, is that which is better at some level is, which is better I think is very interesting because I'm very interested in whether PDE corrected models can compete with pure machine learning models. I'm very interested in that abstractly. I have the impression that we can't judge that from plots like this right now because it kind of depends a little bit on how much effort the people that were training it put in. So, okay. So, intriguingly, the best models at the current time include both pure ML models, GraphCast and GenCast. This is deterministic and this is probabilistic, and a hybrid model, which is what I'm going to talk about today, in which the learn component is part of a traditional dynamical core. That's what the Neural GCM is. And this, as I will tell you, is one can run as either a deterministic forecast or an ensemble forecast. So, and I think it's pretty interesting, actually, that these two are at the top, and it, getting to my meta point, it's a pretty interesting state of affairs right now. Okay, so how do you build AI weather models? So basically what you do is you train them on data, and so there's of course sparse global observations of measurements of the weather that are being made from various types of entities. These are assimilated. There will be talks, and there are people who know much more about data assimilation than I do, into a physics-based weather model. So you basically take this data and find the best instance of a physics-based weather model that agrees with all the data. Then this is basically by ECMWF run on a uniform grid over some time. So this is hourly between 1940 and 2025. This is the horizontal grid, this is the vertical grid over some large number of variables. And this is just an amazing data source that ECMWF has provided. And this is basically what we all use to basically train models. So ML-based weather prediction, and I'm going to just, this is going to be talked about more in a bit. But the deal is that what you do is you take an input weather state at some time, you take the predicted next state at some later time. A typical time difference between the two is 6 hours, and you simply ask to learn a function that predicts the next time as a function of the previous time based on all of the data that you have. And of course, there are a million ways that you can do this. Some are better than others. This is what we've learned over the last couple of years. But fundamentally, the time step here, I want you to, is 6 hours. 6 hours is actually a pretty reasonable time step for a physical process because, I don't know, in 6 hours the weather will be different. So you would but it's not, it's still correlated with the current weather. So it seems like if you were going to choose your time step, that would be a reasonable time step. The deterministic models that are trained this way tend to blur at long times, although GenCast, probabilistic models, and the only example that I know actually, although I may be out of date, is GenCast that apparently solves this issue. So that's the deal on these. So physics-based models solve the equations I was telling you about before from the MIT GCM. There's a set of PDEs that I was trained to love when I was a child or something like this. And you just solve them, but then there are these right-hand sides that I pointed out, and these right-hand sides parameterize huge numbers of physical processes, and these are 100,000 lines of code. And I guess I want to point out two challenges with respect to this. So one is I've already hinted at is that the physics parameterizations are very hard to tune. And in fact, they have not been tuned in the same systematic way that we've seen from, for example, machine learning models. And the other is that when you do physical simulation, and this is something that those of us who've lived in this business for a while are quite aware of, there are annoying constraints on numerical solvers that you can't get rid of. And the one I'd like to highlight is the CFL condition. So the CFL condition is the constraint on how big your time step can be. And the thing that's annoying about it is it has nothing to do with the physics that you're interested in. In fact, by construction, it doesn't. It's a much shorter time scale. So for example, our Neural GCM, I mean, we're taking 12-minute time steps, not 6-hour time steps, and we have no choice. It's grid dependent too. And so whereas the machine learning got to take the step that you'd like, which is appealing. So the hybrid model, which is what I'm going to talk about, the Neural GCM, the idea is that what we do is we write down the same equations that were being written down that, in the physics models. And then what we do is we rewrite them in JAX, which makes them both differentiable and acceleratable. And we then take all of this and we simply learn it from the data from ERA5. So instead of learning the whole thing, we just learn the right-hand side from ERA5. So what's interesting about it is, at least to me about doing it this way, is that there's an inductive bias, as it were, that's in the terms of these equations that we know is correct. We know the Coriolis force is going to do things to winds. We know about advection. If there's a velocity field, the fields will be advected by those fields. And this is built into the solver. There's no uncertainty in them, just like there's no uncertainty in the physics. You don't have to learn them. So that's the good side. So that means that the right-hand sides, like all of these forcing functions that you're learning, are simply taking into account the parameterizations of process that we don't know, and this is what we learn from data. The challenge of this, and there really have been substantial challenges, we weren't the first to try to do this, I'll tell you a little bit about that story in a minute, is that you have to rewrite the code differentiably in order for it really to work, and also you're then stuck with the constraints of the physics model, like the CFL condition, and it makes things complicated. But I mean, the question is whether you get anything out of it, right? Like, I mean, getting back to my philosophical question at the beginning. So, okay, so let's see. So I guess I've now sort of covered these 2 points. Right, I mean, maybe one thing to say about physics-based models, I mean, the best thing that you can say about the laws of physics is that they're infinitely generalizable. That's why physicists love the laws of physics. They pretend you don't have to study anything because you can just go solve the laws of physics. We all know that that's a fallacy, but that's the way it's supposed to be. But they're infinitely generalizable. So if you change the planet, no problem. You just change the equations. But of course, that is, pure ML models require training data, and hybrid things are supposed to be in the middle. So okay, so there has been work to try to train hybrid models before, but they were what I might call offline. And the way they were done, and for example, a major proponent of this is Chris Bretherton from the University of Washington, and is now at one of the Allen AI institutes, is basically to take a traditional dynamical core, which is non-differentiable, and to simply, in every vertical column, to correct the tendencies in it using a neural network. So you could say, I'm going to fix some process by using a neural network, and I'm going to just add it to the right-hand side, right, of the equation. But the thing is that because the dynamical core, the original dynamical core, is not differentiable, you can't train. You can only do this by training through one time step. And so the way that you would do it is you would train the term over one time step, or over many examples of one time step. You'd have many time steps, right, where you've trained it. And then if you wanted to find out what happens, you roll it out over many, many steps. So the problem with that is that, so this, it turns out, actually people tried this for a while, and it just turned out not to work. And actually, there's a beautiful article, kind of a blog post by Stefan Rasp on this, which I think really explains nicely what is going on here. And I think that this is a very general insight, actually, is that his point is that what you're then doing is you're optimizing for improving tendencies. Note that since you're doing this in the context of a PDE solver, you're constrained with what the time step can actually be, right? You can't make this time step 6 hours because the thing will blow up. The underlying code will blow up. And so you're constrained by the dynamical core. And so what Stefan basically points out is that what you're doing is improving like the short-term local thing, but you're not matching long-time statistics, which is what you would actually want, even over 6 hours. And so because of this, this led to, just empirically, unstable simulations and drift, and basically no one managed to make this work. So our team within Google Research did manage to make this work, and the way that we did this was by writing a differentiable dynamical core. So we rewrote the dynamical core in JAX. It's a spectral core, and by doing that, then we have the one-step thing. You can add a neural network to every column, just like was done previously. Our neural network is not very complicated on the scale of neural networks. It's just sort of multi-layer, and it's not very complicated. It's got, whatever, 8 or 9 layers or so. But the point is that what we can then do is we can roll it out over many steps, and we can train over the entire thing. So that means you're not just training on what the tendency of the physical term is from one time step to the next. You're actually you're training on the consequences of that when rolled out over time. And we tend to roll out 3 to 5 days. So if you change the something which is affecting the radiation scheme, you're not just looking at what that will do locally to that term. You're looking at its consequences on the dynamics over a longer period of time, and that basically gives you more information about what's happening, and sort of makes the training, well, empirically makes the training work. We trained it on 3 to 5 day weather forecasts using ERA5. Here's a kind of block diagram of the way it works. We have a dynamical core. We have neural networks replacing the parameterizations. We put inputs, we get outputs. We also put in forcing. We put in noise, actually, as well to generate to generate ensembles. The forcings, though, are not just noise. The forcings are like the sun. We put in the things having to do with the Earth rotation, which are fixed in time, and that's the deal. And then this is TPU GPU native. It's based on JAX's sort of magic of JAX, which is used in many ways. And I'm not going to sort of belabor this, but there's a lot of computer science. So as soon as you decide. One of the nice things that's happened with respect to differentiable programming in the last 10 years. So 10 years ago, there was this package called AutoGrad, which was the precursor to JAX, actually. In fact, I think most of the people who invented AutoGrad are now at Google working on JAX, or at least they were at some point working on JAX. But AutoGrad basically was a wrapper, an auto-diff was wrapped around NumPy, but it didn't allow vectorizing, checkpointing, parallelizing, XLA compilation. And now, because of the importance of languages like this, of libraries like this for machine learning, these things are highly efficient, and they're also open sourced. And so the scientific community can use them. So that's what we did. So I've just told you how to train it. Now, ensemble prediction is also part of modern weather forecasting. We're going to learn about that today. As well. And in this, basically, the point is that, you could start out from a particular initial condition and integrate it in time, but of course, there's an uncertainty in the initial condition, and so what you should really do is consider a cloud of trajectories starting from near this point, and then you should look at the cloud of trajectories that it ends up with, and so then when you look at what happens at later times, you should be, doing something like looking at the mean of the cloud or something, not just starting with certainty. And so this is something that that kind of is natural to include so maybe I say this. So the Neural GCM, the deterministic version of the Neural GCM doesn't smear things out over time. And so because of that, it was relatively simple for us to create an ensemble, because all we do is to give it initial, put in a little bit of randomness initially and let it roll out for different periods of time. So because of that, it's also possible to actually train an ensemble. So the way that you train an ensemble, I sort of described the training of the deterministic model. What you do is you start out with the model, you integrate it in time, and going back to this figure, you train the neural network parameters to match some loss function, which is basically about the accuracy of the network. So what you also could do is you could start out with a cloud of solutions on this side, and then train the neural network. So, for example, the mean of the ensemble, basically, of the cloud as they roll out matches an ensemble mean or something like this. You also could, or you could use some other loss function. And actually, I'm not going into a lot of detail here, but you can train on an ensemble loss function, and I think the most elegant version of the Neural GCM does that. I will answer questions about that if someone has it, but I'm going to just say that for now. But anyway, here are 3 movies of total water column between 0 and 15 days. One of them is ground truth, and 2 of them are ensembles of the Neural GCM, just to freeze it. So this is at 5 days. And what you can see is one of these is ground truth, and the other 2 are members of the ensemble. You can see that they're slightly different from each other. And then this is 15 days. They're slightly different from each other. And so the answer is these 2 are ensemble members of the Neural GCM, and this is the ground truth from ERA 5. And this is the ensemble mean from ERA 5. So you can see how ensembles go. So the interesting thing about the Neural GCM, and actually, sorry, I'm actually worried that my order is something I'm wrong. No, I'm okay. Sorry, this is slightly out of order. I didn't mean to have this here. Okay, so the Neural GCM beats ECMWF's ensemble on most metrics up to 15 days. And so this and GenCast were the first models to beat the ECMWF ensemble up to 15 days, which I think is a pretty interesting accomplishment. So here is so here's RMSE. So this is ECMWF high res is this orange curve. That's a deterministic model. The green curve is GraphCast, which is also a deterministic model, which is better than high res, which is the fact that the green curve is lower than the orange curve is really interesting. The ECMWF ensemble is this kind of grayish curve, and the Neural GCM ensemble is below the grayish curve. And on most metrics, the Neural GCM beats the ensemble. So Stefan Rasp has put together this really wonderful benchmark called WeatherBench 2 that essentially combines many of the important quantities that one would want to measure as a function of lead time from comparing forecasts. And this basically compares physical models, ML models, and hybrid models against each other. This is as a function of lead time from 1 to 10 days. So you'll notice that blue here means that the number is better than RMSE in IFS high res, and red is worse. So this is compared to HRES. But the ensemble mean, you'll notice, from IFS, from ECMWF, is actually better, beats also beats HRES with enough lead time. That's what I told you. That's the point I was telling you about the Lyapunov time of the weather. And what you'll notice is that the Neural GCM on this plot really does very well, as does GraphCast. These are the 2 that do the best on this plot, basically relative to the others. And both of them beat the ensemble. So one can also create probabilistic forecasts. And this probabilistic forecast also includes GenCast, which is a different type of model. Remy, I hope, will talk about it because it's really interesting. And basically what you see there is that both the Neural GCM and GenCast beat the IFS ensemble on multiple things, which I think is really an accomplishment. I mean, because this is both are much faster than the ensemble, and both are using elements of machine learning. And this is out to 15 days. So the interesting thing is, and actually maybe now just going back to this, the Neural GCM and I also GenCast. Remy, sorry, this is the part of our talk, which is we should be giving like 2 parallel talks at the same time or something. Anyway, so also predicts accurately distributions of tropical cyclone track. This is 5 days tracks. This is the ensemble of tracks. This is the ECMWF ensemble 5 days before Hurricane Laura, and the black is the real track. So, but the interesting thing is that the Neural GCM also makes accurate predictions at longer timescales, and this is what we've gotten quite interested in. So the question is, so we're used to predicting the weather out to 15 days, but there are lots of problems in the world where it would be nice to have some sort of a probabilistic forecast of the weather or climate, let's just call it somewhere between weather and climate, out to, say, a year. So, for example, please tell me when the monsoons will hit India 6 months out. Please predict the characteristics of the hurricane season wherever you are in the world 6 months out. Please predict extreme weather events. Where, are there going to be heat waves? There are lots of problems that affect humans that, we're sort of not used to the idea that there could be predictive models that were accurate, very far out. And the question that we've been trying to explore with this is to what extent can one do this already, and can one make it do that? And I guess what I'm here to tell you is that it works just even out of the box surprisingly well. So if we take the Neural GCM, which is trained on weather, and remember what I told you, it was trained on 3 to 5 days of ERA5, and you then prescribe sea surface temperature. So you have to, there's no ocean model, this is just an atmospheric model, but you prescribe the sea surface temperature, and then you integrate in time, so this is sort of trained up till the end of 2019 and starting to predict 2020. This is the global mean temperature, over the next year. And these are the sort of different members of the ensemble from the Neural GCM, and this is the ensemble mean, and that's the comparison between the ensemble mean and ERA5. And so, it's able to predict the variation a year out. The Neural GCM near-term climate forecasts, have less bias than a global storm resolving model, which is the usual way of doing this. So this is a model from NASA called GFDL X-Shield, which uses a lot of computers. This is a coarse-grained Neural GCM, and the bias, the RMSE for precipitable water is actually lower from the lower resolution model, Neural GCM model. This thing runs at 70,000 days per day on a single TPU. This thing runs at 19 days per day on 13,000 cores. So it's a big difference in cost. The Neural GCM, if you ask 1 year out for the distribution of tropical cyclones, the ground truth, this is ERA5, and the blue is the Neural GCM. And what you see is that it's doing really well 1 year out. Actually, Remy, now that I have you, so I've been trying to convince them, and I'm saying this in front of everyone, that we should have a thing. We should predict this for 2025. And we should do it now and save it to some directory with all of these models. And then we can come back next year and report. That would be a good experiment, sorry. Just for fun, just because this is, it's backward looking, but there's no leakage. But I'm not doubting this, but it's really impressive, I think, that this works so far out in the future. And let's see, the Neural GCM also predicts global mean temperature as a function of years better than atmospheric only climate models, which is the sort of natural thing to compare about. So, a simple model that trains the right-hand sides with only 3 to 5 days is able to apparently, not only do well at short time scales, but also predict longer time scales, with some accuracy. This is something that's actively under development. So just to recap this part of the talk. So the technical challenge of the Neural GCM was training the parameterization over long enough times that we could include the effect of the parameterizations as part of the training. And this required software engineering magic that I think is only possible because of the ML revolution. And in that I would count both JAX and that thing that I told you about, all the steps that are required, and also just amazing human software engineers who are able to code this thing. So up to 15 days, the Neural GCM beats the ECM-WF ensemble and is more efficient. Remy will talk, I think, about GenCast. At longer times, the Neural GCM still makes accurate predictions. And I think this is really interesting because we don't know how far this goes out. Of course, for it to go really far out, you need ocean models and land models and things like this, which are going to take a lot of work to put together. But even in the medium term time, predicting a year out is an interesting problem where we have a lot of data. It's not exactly climate modeling, but it's an interesting problem. And I'm really very interested in knowing what is possible to predict. Is it possible to accurately predict the probability distribution of tropical cyclones 1 year from now, or predict the distribution of other extreme events? So finally, what I want to say, and this is, I would welcome anyone to argue with this because I just don't know the answer, is that I think what is predictable at all is very much an open question right now and is rapidly changing. Certainly I think if you had asked me a couple of years ago if one could accurately predict the probability distributions of cyclones 1 year from now, I would have said that seems impossible. But now it seems quite manageable. How one would do these predictions, either hybrid ML versus pure ML, is, I think, very much an open question, getting to my comment about ODEs and PDEs at the beginning. So my take on this at the moment, and again, I welcome discussion, is that I'm not convinced that we know whether either of these is better in any circumstance. My personal feeling is that the ones that are better, I mean, with respect to, for example, long-term prediction, just to use the thing that we've been working on, the reason that it might be better might be because we've been working harder at making it better, right? Like, not because there's some intrinsic thing that one is better than the other. And the reason, again, to get back to my meta point from the beginning, that I think this is so interesting is because many of us were trained with the idea that the laws of physics were sacrosanct and were important for making predictions of complex systems. And this is getting right at, is falling right in the, is that really true, right? Which, if it weren't true, then, you know, the way that we would think about mathematical models anyway going forward is quite different. So, okay, so that's it on the Neural GCM. I have 20 minutes left? Is that right? Something? 15 minutes. Okay, I have 15 minutes left. Okay, that's good. So I only have a little bit of time. I'm going to talk about a different problem. I apologize. But I think it's an interesting problem, and I think it brings up the same issue. I'm going to talk about the problem of learning force fields from experimental data. And this gets to the comments I made about AlphaFold at the beginning. So we've been working on this. In particular, there's a graduate student who I will introduce you to a minute named Ryan Kruger, who spent his PhD thesis doing this. And the thing that he's been focusing on is DNA structure prediction. And the DNA structure prediction, this is just the example problem to go after. There's a lot of data. The models are somewhat simpler than those of proteins, but there are lots of there's lots of examples of DNA outside of biology that's used in technology to try to go after. And basically, because of this, there are people who make force fields for DNA. And in particular, the one that I want to talk about, and the one that we've been thinking about, is a force field that was made at Oxford, which is called OxDNA. There's a rich ecosystem of OxDNA, which is a model of DNA. And the way that it works is basically the following. So what you do is you take every nucleotide and you replace it with a rigid body. So these are images of the rigid bodies, and then you basically you stick them together, and you let them interact basically. And so there's an energy function in this which is physically interpretable. There are cross-stack interactions, and there are vertical stack interactions. There are backbone interactions. There are all kinds of interactions, and this leads to about 100 parameters in this model, which was just invented, that one needs to fit to try to make it into an accurate model of DNA. And so when the people at Oxford first put the model together, there were 3 classes of experimental data that they used to try to fit this. One is structural, like, what is the structure? I mean, what is the ground state structure of a given DNA strand? That's sort of like the protein structure problem. But they also used data that is both mechanical, like, for example, if you take it and you stretch it, how stretchy is it? There's lots of experimental data on that. And the other one where there's really a lot of experimental data is thermodynamic data. For example, what temperature does it melt? Things like that. And the idea was to basically fit these parameters to these classes of data. And so this is a hard problem. And if you go and you look at Tom Aldridge's PhD thesis with the original parameterization, he basically, I mean, this is a quote, and it's not clear what else you would do. The stacking strength and stiffness were altered by hand. Hydrogen bonding were added and adjusted. Things were adjusted by hand. So it was very much of a hand-adjusted, here are my 100 parameters, this is what I have. And there have been a series of releases of OxDNA to sort of improve the parameterization, but this is vastly different than what we were just talking about with respect to parameter optimization on weather models, and it's also vastly different than what's done typically in machine learning models. And so the question that we wanted to ask is whether or not it was possible to fit force fields to experimental data directly. That is, can one do this? I mean, again, we know the equations of motion. It's dx dt equals force plus noise. That's the equations of motion. It was handed down by the gods. That's the equation. That's what you learn in physics. And the force, well, you can parameterize the force, and can you just fit to the data? And so this is mathematically the same problem that I just described with respect to the weather. It's just put in a rather different thing. So this is Ryan, who did this for his PhD thesis. This is Megan, who was a postdoc who knew a lot about OxDNA. She's now a professor in Alberta. And we basically tried to go after this. And the way that we went after this is very much like what I told you about the Neural GCM. We rewrote the equations in JAX. It was exactly the same thing. We rewrote the equations in the JAX. We then tried to fit. We then found that it was impossible for the same reason as I'm about to show you. And then we figured out what to do. And now I think we know how to fit. So the key technical problems in doing this are similar to the Neural GCM. So on one hand, we want a better model of force fields. Newton's laws implies that this updates the rule from one configuration to another. So that's what force fields do. On the other hand, if you think about the experimental data that I just described, they don't give short-time updates. There is no data on, you can't take movies of DNA flopping around. If you're going to heat it up, if you're going to put like the same strands in solution, so you have double-stranded DNA with some sequence, and then you heat it up and you measure the melting temperature, you can do that. You can measure the melting temperature for lots of sequences. You can do that. But that is a very different experiment than what we're measuring here. So if we did have this data, we would still have trouble without a differentiable model, but with a differential model, we would be okay. But we don't actually have the analog of ERA5 for this, and there's no way we ever will. And so instead, the only way to do this is to fit to bulk thermodynamic experimental quantities. And if you think about what is required here, it's really a mess. So for example, for any of you who have ever thought about this before, if you want to calculate melting temperatures, these are extreme events. So you actually have to accurately compute the probability distribution of extreme events. If you're going to optimize over them, then you have to do that. And so basically the point is that what you immediately run into is the idea that memory and compute constraints for optimizing are severe in much the way they were for the Neural GCM. And so the basic approach, which is one would like, is there's some input parameters, there's some output parameters, there's a simulation. Basically doesn't work. It doesn't scale. You run into trouble. And that is, in order to run, so you need to include many simulation steps to match even basic structural properties. Because remember, these things are noisy. If we go back to the simulation, it's like bouncing around. That's what it looks like. So if you want the structure, there isn't one structure. It's fluctuating about the average structure. So you have to actually average for long enough that you actually get the average to converge. And then that means you have to simulate for a while if you want to fit it. It's not a zero temperature thing. And then you basically, the memory blows up, the gradients blow up, the time blows up, but we tried it anyway. Actually, Ryan has what is the word? Nerves of steel. He's willing to try anything. He did it. He tried it. So this was an attempt to basically optimize over the pitch, and the averages here were computed. I mean, just to sort of remind you of how this would go. So if you're doing a simulation, what you do, remember, is the time step of a simulation is constrained by the simulator ability. It's again this stupid CFL condition thing. Sorry, the reason I'm being emotional about a condition is because, for those of you who have thought about this, the numerical time step condition for stability does not have anything to do with the physics that you're interested in, which is extremely annoying. And so in particular, the subsequent states that come out are highly correlated. So what we do, and what everyone does, is to throw out all the data, keep every 100 time steps, because then at least they become somewhat decorrelated. And then we sort of run the remainder over 50,000 steps with 10 batches, and we used the limits of what we could compute, and we tried to basically fit the pitch of a 60 base pair duplex. This is the correct pitch, and this was the result of our gradient descent algorithm, and it just didn't work. But then we came across an idea, and maybe this is the last idea in this talk. Maybe this is the best idea in this talk. This is an idea that was not invented by us. It was invented by these people, Thaler and Zavadlav. And their idea is called trajectory reweighting. This is a way to basically make this thing work. And their idea was basically the following. So what you're actually interested in is the time average of an observable. So that's what I just described, like the time average of the pitch, for example. So what do? You do what I said. You sample, you subsample, and this is every 100 time steps. And this time average converges to the equilibrium average if you average enough. And so that's what we want. But what we then want to do is take gradients with respect to this. And the problem is that if you change the parameters theta, that is the parameters underlying the model, then you both change the samples. You really have to redo the whole thing from scratch, because you've changed the parameters, so you have to redo it from scratch if you want to compute the average this way. But what these guys realized is that in fact, to leading order, if you're not changing theta very much, you can just think about the average of the observable as a sum of weights times the observable, where the weights initially are 1 over n, but the weights, and this comes from thermodynamic perturbation theory, an idea from a long time ago. Just, that basically these weights are the ratio of the probability of the new parameters theta divided by p of theta hat, where theta hat is the initial configuration where you sampled the things from. And the beauty of this is you don't, as long as you don't change theta very much from theta hat, you don't have to resample. So you can generate the configurations initially, and then you have a formula, and now you can take the gradient of this formula, and you can update it for a bit. And then every once in a while, you can update the samples. And so the real beauty of that is that once you do that, now you don't have to use a differentiable simulator anymore to generate samples, which is really very important because although I didn't emphasize this, these JAX-based simulators aren't as fast as the C++-based simulators that have been developed by the computational physics community for a while. And so we literally use lamps to basically generate these samples, but you can then use JAX to optimize through them. And when you do this, everything works. It's really cool. It's kind of a similar idea to what I was describing with the Neural GCM, except that this is even pushing it further. Anyway, I'm running out of time, and I knew this was going to happen. So we do this, basically. And when we do this, then basically, I don't know, I don't have time to go through this. Basically, everything converges, basically. So we can tune the potentials to match pitches. This is pitch. This is actually an example of a structural optimization. This is a structure of some DNA thingy that people are interested in, and we simply matched the potential. We took the potential parameters and we updated them to decrease the RMSE between the predicted structure from Ox DNA and the target structure. So what you really want to do is do this, to get to the AlphaFold example, is you want to do this over a massive set of structures and to simultaneously optimize over all of them. We didn't do that, but we at least showed that this worked on one, which, as I said, was a computational challenge. We fit to mechanical data. Fitting to mechanical data is interesting because you have to fit a force extension curve. You have to actually imagine force versus extension. And so the DNA is actually what physicists call a worm-like chain, so there's a functional form that you have to fit. And so what we do is we actually compute the average at 3 points, and then from those points, that's enough to uniquely determine the worm-like chain model, and we then optimize through the parameters in the worm-like chain model using this whole thing, which is kind of crazy. But it lets us optimize for the persistence length of the DNA. We can optimize for other parameters. I don't have time to go through this. We can optimize for thermodynamic parameters like melting temperatures. This is also a mess. I don't have time. I'm sorry, my talk ran out of steam. But you can fit to melting temperatures. And then, once you know how to do this, you can sort of go off and extend to other systems. Ryan's been busily working with Peter Solch on modifying models of RNA. These are DNA protein complexes. And then, even there's a famous package which is called Martini, which is about simulating lipids, where we've been working with the lipids developers to actually improve those too. And this is all very early in the sense that, maybe the bold-faced thing. What we have not done is used any of this to make a truly amazing model of anything. You're like, oh, I did it. So here's my amazing model of X that you can now go use. We haven't brought that to the end, but I feel like we've de-risked the technical challenges, and we at least know how to do this now. And so we sort of solved the technical challenge of force field fitting with experimental data, which I think is a very important problem more generally. At least, assuming that that ODEs will still exist, that these physics models still exist in 10 years, that this seems very important. Just because it's the way to interact with experiments in a substantive way and to really, have a loop between, experiment and computation and theory. So what is needed basically to be able to make a truly amazing model of anything? So part of the reason that we didn't do it is because we just didn't do it. But the other reason is that one really needs a large-scale data collection effort to be able to compute dynamical properties. The thing you should keep in mind from both the weather climate example with ERA5. ERA5 is an amazing data set. AlphaFold, the PDB, is an amazing data set. Without these data sets, there's you can't fit to you can't have this competition of models and whatever. And for these problems, the data collection doesn't exist. One thing I'm worried about in general is that I don't know how the data collection is ever going to exist on some of these things. The scientific community, well, I mean, at the moment, the United States, the scientific community is broken, but in general, the scientific community isn't really organized to basically create large-scale data collection efforts, which I think is needed if you want to make better models. I think that this question that I started this talk with, which is to compare pure machine learning models to physics ML hybrids, is very interesting in these problems too. And I mean, one could play the same game that we were playing with pure machine learning models, we just didn't do it, and see who would win. And I basically think, again, just to repeat my position on this, is I think it's impossible to tell without trying it. And just to say, I think that this problem of which type of model is better in different situations and to really understand when and why I really think is one of the great mathematical, it may be even the great mathematical modeling question of our time, because there are different structures of models which have different types of inductive biases, and everyone's running around talking about all of them, but we kind of need principles. And I think that this is really what's been driven by the ML resolution. So to recap, and then this is my last slide and then I'm really done. So I think that, to my mind, we're in a much better position to use solutions of dynamical systems to predict complex aspects of the world than we were 5 years ago or ever in my scientific career. I mean, I've basically spent my entire scientific career trying to solve dynamical systems and then to use them in some way to influence experiments. And I don't think it's been very successful. I remember, just as a story, that there was a chemist at Harvard named George Whitesides, who for a time was the most famous chemist at Harvard. He still would be, except he retired now, so I guess he's no longer there. And I remember around 2010, he was kind of grumpy, and he said to me, I really like having you around. You're a good technician. And I was like, well, what do you mean? And he said, well, whenever I write a Nature paper, I need a figure that basically has a modeling model in it. And I just ask you for one, and you always provide one. Which, it's kind of insulting, because it's like, well, but I didn't contribute anything to your understanding. But he was kind of right. That is, without accurate models, if you're studying actual things, it just doesn't work. But I think it's now, for the first time in my scientific career, I think it's possible to go after this. And for theory and computation to be first-class citizens, I think we've seen this from AlphaFold. I think we're starting to see this for weather and climate, and we'll hear more about this today. And I think it's really exciting. I personally believe, and it says I believe in quotes, this is almost a religious belief for me, I have to believe this, that dynamical systems based on physical laws will give the best possible models. But I actually have no idea why that would be the case. If anyone here does, then we'll have to know it. I think it has to be explicitly proven empirically, and that we're now in the midst of trying to figure this out. And finally, weather, climate, and force field are only 2 examples. There are lots of examples of these things. I'm not going to, and I want to just end. So this is Ryan and Megan. This was my research group at Harvard a couple of years ago. And these are all the people in Google, in DeepMind, MIT, and ECMWF that worked on the Neural GCM. So these are really the people that made it work. Thank you. I hope that was somewhat coherent.